Section: Introduction. Let's delve into the fascinating world of human intentions and how they influence our actions. We often act based on our understanding of the environment and the mental states of others. For instance, consider a scenario where Tom's friend Anne is searching for her backpack in the office. Tom, knowing that the backpack is in the kitchen, would suggest Anne to look there. This proactive behavior of Tom is based on his understanding of three things: Anne's objective to find her backpack, his knowledge about the backpack's location, and Anne's mistaken belief that the backpack is in the office. Tom realizes that Anne's incorrect belief is preventing her from achieving her goal, and his intervention could assist her. This ability to understand and act based on another person's beliefs, intentions, and emotions is known as theory of mind, Tom, a crucial aspect of human social interactions. With the advent of large language models, LLMs, there has been a surge in research exploring their potential for Tom capabilities. Most of these studies use established psychological tests like the false belief test. While these tests measure LLMs' ability to infer mental states from given scenarios, they often overlook a key human ability: acting based on these inferred mental states. In other words, humans often act based on the intentions and beliefs they infer from others. However, despite performing well on the false belief test, LLMs often struggle to determine the most appropriate actions in scenarios that humans would find straightforward. This is a critical consideration for the development of future AI agents, from virtual assistants to embodied robots. To address this, we introduce a new evaluation paradigm called Thinking for Doing, T4D. This paradigm tests whether models can decide on appropriate actions based on the mental states of others, rather than just answering questions about these mental states. In T4D, models are seen as agents that process a series of observations to determine the most suitable action from a set of options. We use stories from a widely used Tom benchmark, TOMI, based on the Sally Ann false belief test, as observations in T4D. This ensures that models must use mental state reasoning, especially when a character is identified to hold a false belief. The novelty of T4D lies in its objective. It requires models to determine actions based on mental state reasoning, rather than just making inferences from it. We found that the best performing model, GPT-4, achieved a maximum score of 50%, while human annotators agreed over 95% of the time. To understand the challenges LLMs face in T4D, we identified three reasoning patterns from human-written rationales: question decomposition, theory of mind inferences, and common sense assumptions. We then tested LLMs in Oracle settings, providing them with Oracle reasoning steps based on these patterns. The main challenge for LLMs in T4D is identifying the correct evidence to inform their actions. When we provided models with specific hints about relevant inferences, their performance significantly improved, approaching human levels. This led us to the question: can we develop a method that improves LLM's T4D performance without providing Oracle hints but instead teaching models to better structure their reasoning process? In response, we introduce a new zero-shot prompting framework called Foresee and Reflect, FaR. This framework guides models' inferences by providing a reasoning structure using future thinking. FaR has two components: Foresee, where it prompts the models to predict future events based on observations, and Reflect, where models reason on which action choice better helps the characters with potential challenges. Compared to other prompting strategies, FaR improves LLM zero-shot performance by as much as 50%. We also conducted studies to understand FaR's strengths and limitations. We found that both foresight and reflection are crucial for tackling T4D and that LLMs are sensitive to noisy reasoning steps about the future in FaR. This makes it an interesting future direction to explore how to help LLMs recover from noisy foresight. We also tested FaR on out-of-distribution story structures and a non-false belief Tom task to see if it overfits on the TOMI converted T4D task. We found that FaR shows consistent improvement across generalization tests, even outperforming few-shot prompting. In summary, our contributions are as follows. We propose Thinking for Doing, an evaluation paradigm to challenge whether models can connect social reasoning to actions. We find that LLMs struggle on T4D, and our analysis indicates the key bottleneck is identifying implicit inference steps. We designed Foresee and Reflect, FaR, a zero-shot prompting framework that dramatically improves LLM's performance on T4D. Our analysis and generalization studies show that FaR's robustness generalizes to diverse contexts. Section Summary. The section introduces the concept of theory of mind, TOM, which refers to the ability to reason about and act on another individual's beliefs, intentions, and emotions. While large language models, LLMs, have shown proficiency in inferring mental states, they often fail to determine the most useful actions based on those mental states. To address this, the authors propose a new evaluation paradigm called Thinking for Doing, T4D, which tests whether models can determine proper actions based on the mental states of others. They also introduce a zero-shot prompting framework called Foresee and Reflect, FaR, that improves LLM's performance on T4D by providing a reasoning structure using future thinking. Section: Background and related work. Let's delve into the background and related work. We'll start with the concept of theory of mind, TOM, and its relationship with language models. TOM, a subject of extensive research in psychology and cognitive science, is often tested in children using tools like the false belief test, FBT. Recently, as neural language models, LM, have shown remarkable performance in language understanding tasks, researchers have been trying to determine if these models also exhibit TOM. They've been using false belief templated story datasets like Tom, Bobby, and Tommy for this purpose. However, these tests have their limitations, including scalability issues and noise in text game environments. Our work focuses on FBT for TOM, a well-studied area, and reevaluates the format of these tasks when testing large language models, LLMs. We found that while some studies suggest LLMs show some degree of TOM, they lack robustness and fail when FBT is applied in more realistic scenarios. Next, let's talk about large language models and agents. Recent research has been focused on creating language agents that can perform actions, which can range from mimicking human social behavior to completing tasks using websites. Our work differs from these studies as we focus on actions that require a proper understanding of other individuals' mental states, TOM. We've identified a performance gap between answering inference questions only and choosing actions based on inferences. To address this, we've designed a zero-shot prompt that improves models' capability to generalize robustly. Now, let's discuss prompting techniques for LLMs. Recent advancements in LLMs have led to a variety of few-shot and instruction prompting techniques, including chain-of-thought prompting, least-to-most prompting, and search-based approaches like tree of thought and RAP. However, our primary goal is not to introduce a new prompting technique. Instead, we aim to highlight the benefits of imposing a structured framework on the LLM's reasoning process, especially in the context of TOM tasks. Our analysis reveals key elements of reasoning that can help LLM agents act, which we've captured in our proposed approach, FaR. Any prompting method that supports detailed, multi-step reasoning and captures the foreseeing and reflecting steps is well suited to handle the complexities of TOM tasks. Finally, let's introduce the Thinking for Doing, T4D, task and its associated data. The T4D task requires models to use social reasoning to choose an appropriate action as a situated agent. In social scenarios, an agent's perspective can be broken down into four main variables: observations, inferences, tasks, and actions. Traditional social reasoning tasks usually challenge models with questions targeting specific inferences. For instance, they might ask a question like, "Where will Jackson look for the onion?" along with a set of possible answers. This kind of task can be represented as estimating the probability of an inference given the observations and the task. However, in many real-world AI applications, decisions often revolve around actions rather than explicit inferences. These decisions are influenced by underlying, often implicit, inferences. To bridge this gap, we introduce T4D, a task designed to assess a model's ability to determine the appropriate action based solely on observations, without being directed towards a particular inference. In the T4D framework, the model's task is not simply to make an inference but to decide on an action based on inferred mental states. This decision-making process involves estimating the probability of an action given the observations and the task, where the inferences act as a latent variable, inferred from the observations to subsequently influence the chosen action. Section Summary. In this section, the authors discuss the background and related work on theory of mind, TOM, and language models, LM. They highlight the use of false belief tests, FBT, to assess TOM abilities in children and the application of neural language models to study TOM. The authors also mention the challenges faced in testing Tom in different scenarios and the focus of their work on false belief tests for Tom. Additionally, they mention the development of language agents that can perform actions and the various prompting techniques used in LM research. Finally, they introduce the thinking for doing (T4D) task, which assesses a model's ability to determine appropriate actions based on observations and inferred mental states. Section: Converting Tom benchmarks to T4D. In this study, we're focusing on a key aspect of social intelligence known as theory of mind, TOM. We're taking an existing benchmark, TOMI, and transforming it to focus on decision-making rather than just inference. To illustrate, let's consider a scenario from the classic Sally-Ann test, which TOMI uses. In this scenario, a character named Owen mistakenly believes a suit is in the cupboard. TOMI would ask us to figure out what Owen is thinking, and we'd conclude that he'll look for the suit in the cupboard because of his mistaken belief. But we want to shift the focus to actions. So, we introduce a new element. Both Owen and another character, Nathan, plan to use the suit soon. By stating their intentions, we're trying to prevent models from simply helping the character with immediate plans. But we also want to make sure this doesn't make the task too complex for humans. In our modified task, which we call T4D, models are asked to decide which character they would help most by giving accurate information about the suit's location. So, in this T4D version, models need to figure out from the story that Owen still wrongly believes the suit is in the cupboard, and that giving him accurate information about its location would be very helpful given his upcoming need for the suit. We've converted around 500 TOMI stories to T4D using a programmatic approach due to TOMI's templated structure. Before we use T4D to evaluate our models, we want to make sure it's valid. So, we tested it with human Tom by randomly selecting about 80 instances and having them evaluated by 20 human raters. We didn't extensively train these raters on Tom tasks or provide any answers in the task examples to ensure the study reflects how most people would use Tom in real life. Our findings show that T4D tasks are robust. Every instance had agreement from at least 17 of the 20 raters. Plus, over 90% of the instances had agreement levels of 95% or higher. This strong consensus among humans shows that T4D's design naturally aligns with human decision-making perspectives. We then tested large language models, LLMs, on our T4D task and compared their performance to the original TOMI set. We used Palm 2 Bison, S, and Unicorn, L, ChatGPT, GPT 3.5, and GPT-4. We found that both Palm 2 and GPT models performed almost as well as humans on TOMI, but their performance dropped significantly on T4D Tom. This shows that T4D is challenging for even the most advanced LLMs. To understand why LLMs find T4D challenging, we conducted a study to understand the reasoning processes humans use to tackle T4D tasks. We identified several reasoning challenges that seem particularly difficult for LLMs. One of these challenges is question decomposition. Humans often break down the overall T4D task into more specific questions. To help models do this, we added hints that highlight specific information. Another challenge is theory of mind inferences. This is the core inference tested in the Sally-Ann test. Can models correctly infer that Sally will look for the item in the old location because she left the room before Anne moved the item? We made this easier by providing Oracle Tom inferences in the observations. The final challenge is common sense assumptions. To solve the task, models must assume that both containers are in the room, even though this isn't explicitly stated in the observations. We made these assumptions explicit in the observations. In summary, we've transformed an existing Tom benchmark to focus on decision-making, introduced a new task called T4D, and identified several reasoning challenges that make T4D difficult for LLMs. Section Summary. This study introduces a modified benchmark called T4D, which focuses on theory of mind, TOM, and shifts the focus from inferring mental states to probing agents' action decisions. The T4D task requires models to identify which character they would assist the most by providing accurate information about a certain object's location, taking into account the character's intentions and beliefs. The study finds that while language models perform well on the original TOMI benchmark, they struggle significantly on the T4D task, highlighting the challenges posed by T4D for contemporary language models. Section: Analysis Results. Let's delve into the results of our analysis. As shown in the figure, giving oracle hints leads to different outcomes across the reasoning dimensions we've identified. When we guide models with hints about item location, which we'll call plus QD, and include oracle-derived character beliefs, or plus TOM, we see a significant improvement in task performance. However, simply clarifying assumptions, or plus CSA, doesn't do much to increase model accuracy. We believe that providing plus QD or plus TOM inferences aids models by offering suggestive evidence. This could be in the form of leading questions or relevant plus TOM inferences. These findings also indicate that the poor performance of language learning models, LLMs, on the T4D task isn't due to the task design, but rather their inability to make correct inferences and reason properly. One of the main challenges for LLMs in the T4D task, which humans find easy, is navigating the vast latent inference space to find the right inference that clarifies which action to take. To address this, we've developed the Foresee and Reflect, FaR, prompting method. Based on our analysis of the T4D TOM task, we wanted to see if we could help LLMs identify an implicit inference path that leads to the correct action choices without hints. Humans naturally identify relevant inferences from observations and make decisions like, who should I provide information to? But getting LLMs to perform similarly structured reasoning is difficult. Even though LLMs can make inferences, they don't necessarily connect these inferences to coherent reasoning about actions. Our solution is to give LLMs a general reasoning structure that guides them to relevant inferences. This is where the FaR framework comes in. It gives LLMs a structured reasoning approach, prompting them to 1. Predict potential future events from given observations, and 2. Think about actionable steps that would best serve humans in real-time contexts. The main contribution of FaR isn't introducing a new prompt, but demonstrating the benefits of imposing a structured framework on the LLM's reasoning process. The first step in the FaR process is to prompt models to consider potential future events. This is based on the understanding that the most helpful assistance often involves shaping a more desirable future outcome. This is related to the psychological trait known as consideration of future consequences, CFC, which is the ability to predict future consequences to inform current action decisions. After predicting likely future events, we prompt models to reflect on whether taking actions now could help with the potential challenges identified in the first step. This process can be seen as pruning the generated potential future inferences based on the available action options. Overall, FaR helps LLMs connect relevant inferences about the future with the intended action choices, completing a reasoning chain that spans observation inferences action. Conceptually, the FaR method is similar to the A** search algorithm, which is used to find the optimal path in a weighted graph. FaR starts with observations and aims to arrive at an optimal action decision. The predictions made during the Foresee step act as heuristics, guiding the reasoning process toward the most relevant inferences. The Reflect stage in FaR narrows down the inferred events based on available actions, similar to how A** prunes paths based on the heuristic and cost so far. We tested the potential of various zero-shot prompting methods to improve LLM's performance on T4D and conducted generalization tests. We wanted to answer 3 research questions. 1. How much can FaR improve LLM's zero-shot performance on T4D? 2. Are both the Foresee and Reflect components necessary, and what are the limitations of FaR? And 3. Does FaR generalize robustly across scenarios where models need to connect inferences with intents? We considered several zero-shot prompting strategies, each offering a unique reasoning structure. These include the chain of thought, COT, tree of thought, TOT, self-ask, and FaR methods. Full descriptions of the prompts are available in the appendix. In conclusion, our FaR method dramatically improves LLM performance and generalizes robustly. Section Summary. Providing oracle hints related to item location and incorporating oracle-derived character beliefs significantly enhances task performance, while merely clarifying assumptions has a limited effect. The low performance of LLMs on T4D is attributed to their failure in drawing correct inferences and reasoning, which can be addressed by navigating the unconstrained latent inference space. The Foresee and Reflect, FaR, framework equips LLMs with a structured reasoning paradigm, prompting them to consider potential future events and reflect on actionable steps, improving their performance on T4D. Section: FaR dramatically improves GPT-4 zero-shot performance. Our research shows that the foresight and reflection (FaR) method significantly enhances the performance of language learning models (LLMs) like GPT-4 in zero-shot prompting tasks. We compared 4 different zero-shot prompting methods and found that FaR was the most effective. It increased GPT-4's accuracy from a base of 50% to 71%, and improved the performance of all other LLMs by between 12% and 18%. Interestingly, we noticed that more powerful models, such as GPT-4 and PaLM-2L, benefited more from FaR. FaR works by combining 2 main components: foresight, which predicts future events and challenges, and reflection, which reviews action decisions. We tested the importance of each component by removing them one at a time from the FaR prompt. When we removed the foresight component, performance dropped by 17 points. When we removed the reflection component, performance dropped by 12 points. This shows that both components are crucial for the task. We also tested the robustness of the FaR framework by introducing noisy or incorrect foresight. For example, we might predict that Sally will enter the bedroom to sleep without any clear reason. This caused the accuracy of GPT-4 to drop from 71% to 42%, which is even lower than the baseline. This shows that while FaR can improve reasoning when used correctly, it is sensitive to the quality of the foresight provided and can actually harm performance if used incorrectly. We also tested how well FaR can be applied to different scenarios. We used 3 challenge sets to test if FaR can handle story structures that it hasn't seen before. These sets introduced complexities like moving 2 items between 2 rooms, involving multiple characters with 1 item, and moving 1 item between 4 containers. We found that FaR helped LLMs achieve the highest accuracy on all 3 tests, for almost all models. Finally, we tested FaR's adaptability by using it in faux pas scenarios. These are social stories where a person says something without considering if it might upset others. We used 20 expert-curated stories and asked the models to choose a character from the stories to provide emotional support. We found that FaR outperformed all other methods, showing its versatility as a zero-shot prompt.